Hi dear listener, today we'll be looking at a project on wind turbine power systems for a Bell telecommunication tower in Mike's Crescent, Newfoundland and Labrador, presented by two engineering students, Saeed Shafi and Omar Kyoda Emmanuel. Our instructor for the course, Dr. Tariq Iqbal, and the course ENGI 9896 Renewable Energy Systems. So here is a brief outline for the presentation. We'll look at the introduction, the relevance of this project. We'll also look at the literature review back in the project and key insights from previous research done on this project. We'll also look at the system design and sizing, the steps taken to achieve this, and we'll look at the dynamic simulations in Homer and MATLAB. Then we'll talk about the results, and also we'll conclude the paper by giving our final takeaways. So usually telecommunication towers which are located in remote areas, in our case at the Mike's Crescent NL, we can see that the telecommunication tower is located in a remote area far from urban activities. This type of telecom towers require a reliable source of energy and preferably off-grid. And in recent times, the major competitors for this has been the diesel generators, which are usually costly and unsustainable. And we propose a hybrid wind battery system to supply the tower's need of 1.5 kilowatt. And why wind? We chose wind for this project because the site's annual wind speed is about 7.78 meters per second, which gives us a great opportunity to utilize wind energy. Of course, we'll also address challenges associated with the use of wind for this location, and its intermittency, the icing that can occur during the cold weather, and also the durability of the system. Let's talk about the literature reviews supporting this project. According to the research done by Kaldelis and Zarifakis, they found that wind energy is viable for telecommunication tower as an alternative source of energy for towers located in rural areas. And also the wind resources for this location support high efficiency due to its high wind resources. Hybrid systems also have been proven to achieve up to 99% reliability, and that's by Mahmoud and Higazi. And we've decided to select the Xerox Skystream 3.7 because of its capacity to meet our demands and its anti-icing characteristics and corrosion resistance, which will be useful to combat the harsh weather conditions of this location. So here's our system design overview. So definitely we'll be including the wind turbine, which is connected to a permanent magnet synchronous generator. And since it produces an AC source, we're going to convert that to DC, which our telecom uses, and then connect that to the DC bus. And for the batteries, we'll use a charge controller because sometimes we can get a higher than needed energy, and we can direct this energy to charge the batteries. And if the load also is not met by the wind turbine, we can also discharge it to charge to supply the telecom. We also have some controllers, the PI for the charge controllers for the battery, and MPPT, which uses the perturb and observe algorithm to ensure maximum power extraction from the wind turbine. And of course, we have all the power electronics, the diodes, and some other protective devices, fuses here and there, also to ensure the wirings to ensure that the system is stable and reliable. So here we're going to talk about the Homer simulation. We first connect the wind turbine to the DC bus and also the battery also to the DC bus, and that will supply the telecommunication tower with our load of 1.5 kilowatt. And the calculation done to choose the size of the batteries, we assume a 4-day autonomy. That means that we assume that 4 days of no wind, and since our Daily is 36 kilowatt hour per day for the demand. We multiply that for 4 days and we get this value, and we divide by the efficiency of the battery and we get 205.71 kilowatt hour. We also take account the discharge rate of the battery and we get to 57.14, and we take account of the volt of the DC bus and we divide by the ampere hour of the battery and we get 16 batteries. Here we highlight the wind resources for this location, and the annual average is 7.78 meters per second. So let's discuss the results from the Homer simulation. We can see that Homer suggests two Xerox wind turbines and 7 batteries to power our system, and that will give us an excess electricity of 30% or 5,779 kilowatt per hour per year, and an almost 0% unmet electric load. And our system is completely renewable with a 100% renewable fraction. For our battery, for the 7 quantities of battery, we get a 58.6 hour autonomy. That matches closely well with what we calculated for 16 batteries for 96 hour autonomy. And so our system should work, and from the system we get an annual generation of 19,139 kilowatt hour, and the battery contributes about 4,251 kilowatt hour and an excess energy of 32.2%, and we can redirect that for the anti-icing system of the Xerox wind turbine. Okay, so we're going to look at the MATLAB dynamic model for this project. We'll start with the wind turbine, the Xerox Skystream 3.7, and we'll feed that with our wind speed data. I will not use a pitch controller for the system because it doesn't have a pitch controller, so we'll set this value to 0. And this the torque is fed into the PMSG motor, which is then rectified by a rectifier from AC to DC, and the DC voltage here is boosted by DC to DC boost converter and then is fed onto the load. The IGBT switch is controlled by the MPPT algorithm, and we'll look at that in future slides. We also have a battery connected to the system, and the battery also works in a similar fashion. We use here a bidirectional DC-DC converter because we can feed energy to the load when there is insufficient load from the wind turbine, or we can also charge the battery when there is sufficient to meet the load and also charge the battery. The switch here is controlled by a BI controller, and that signal is fed into the switches here, and the signal from the MPPT controller is fed directly to the IGBT switch. We have on the right here some measurement tools to monitor the performance of the system, the power measurements, also the DC volt bus voltage, and also the battery measurement. So in the initial model, we varied the wind speed from 2 meters per second to 10 meters per second, and as the wind increases, the wind power also increases. So at the initial state it is at 0 because this is below the cut-in wind speed of the turbine, so no power is generated. The rotor speed also varies as the wind speed increases. The load is met at all times because when there is not enough power from the wind, we discharge the batteries to meet this the demand of the load, and then when there is sufficient, this discharge is discontinued. The bus voltage is maintained to ensure this system works. So let's have a look at the MPPT control system for this project. It is modeled after the Perturb and Observe module algorithm, and its schematic is shown in this figure here. So basically the MPPT controller here feeds the impulse to the IGBT switch to regulate the DC voltage produced at the output here. We do this by measuring the voltage from the rectifier, which is fed via this input here, and it's fed into the MPPT algorithm, and also the current from the rectifier is also fed into the MPPT controller. So we measure this and calculate the power and regulate this following the schematics of the Perturb and Observe to ensure that the voltage is not exceeded, and we adjust this duty cycle based on changes in the power from the rectifier and the power that we require. Of course, again, one of the scenarios before we talk about the results, when the power from the wind turbine exceeds its rated maximum, the MPPT duty cycle increases tremendously, and the DC voltage drops, and then completely shuts off flow of current to the load to protect our load. Conversely, this will work too if we increase the load to our calculated maximum. If it's increased beyond the rated maximum, the system will act in the same way by shutting off the IGBT controller or disconnecting it to protect the load. And from this system, we've proved that our system meets the 1.5 kilowatt demand with a reliability of 99%, which is the theoretical reliability. The excess energy which we got can be used to help protect against icing. The limitations of our system is that we did look at the cost, but not in real terms, and given current situations and the changing market, the cost that we realize here doesn't really take into account changes in market price as of today, relating to inflation and any other unforeseen circumstances. In the future, it will be great to have a solar PV integrated into the system. This will ensure a more reliable system, and also maybe reduce the cost on batteries for the system. So in conclusion, the hybrid system meets the 1.5 kilowatt demand with high reliability using the wind and the battery system. The MPPT boosts the energy capture and also protects the load from unforeseen circumstances. The excess energy, as shown from Homer, can be used for anti-icing in harsh NL Newfoundland winter's condition. Homer and MATLAB confirms the feasibility and stability, and we're able to achieve our goal of dependency on the grid, and of course looking forward to a diesel alternative, so our system is more reliable and greener and able to meet the demands of this telecom, which is remotely located. For future works, we suggest including a more detailed cost analysis or the inclusion of solar into the system, and also real-world testing to see how the system works in real world. At this point, we want to say thank you for listening, and I would like to show appreciation to Memorial University of Newfoundland and also to its indigenous people. We'll also like to thank our professor and instructor, Professor Tariq Iqbal, for its guidance throughout this course. His input and guidance has been of tremendous help. And we'll also like to thank you for listening to our project. Have a great day.